There we go. All right, so we left off actually on problem 17.8, and then we did a practice problem when we were calculating a weak acid and strong base titration, and we had worked through and done some work where we showed the fact that the concentration, in this case, of the weak acid when reacted with the strong base, you saw that the strong base here was completely consumed in this case, and it consumed that equivalent amount of the weak acid. So we were only left with a small amount of weak acid left. And then we also had the equivalent amount of the conjugate base of the weak acid. We went through and calculated the molarities of each of those, plugged that information into the Ka equation, and then solved for our proton concentration to calculate our pH. Right. So now we're going to just kind of take a closer look at the equivalence point, and we're going to calculate the pH at the equivalence point. So remember the equivalence point, that's the point at which the acid and the base are equal in concentration, right? So, and we're going to take a look at the pH for this example. If you recall, there was, let me go back, several problems that go, right, when we did strong acid, strong base, right, with a strong acid and a strong base, our pH at, oops, I'm not in presentation mode here. My bad. We're strong acid and strong base here, right? When we look at the equivalence point, right, at the equivalence point here, we had a pH of 7, and that was because, you know, with strong acid and strong base, you had complete ionization of both the acid and base beforehand. So it essentially is just a reaction of protons, right, plus hydroxide ions, and they just form, you know, they're just in equilibrium with water. And right, the pH of this reaction at the equivalence point is just the Kw equation, right, where Kw is equal to the concentration of the acid times the base. Well, with a weak acid and a weak base, oops, it'd be a little different, right? Because now we're going to have an equilibrium that occurs once this reaction, you know, is completed. So we'll read through the bullets on the slide here. It says, because the neutralization of a weak acid produces its anion, a conjugate base that can react with water, we expect the pH at the equivalence point to be greater than 7, right? And the reason for that, right, is because that conjugate base is going to react with water to produce hydroxide ions, right? The initial number of moles of acetic acid equals the number of moles of acetate ion at the equivalence point. We'll go through the calculation to show this equivalence. And then we use the volume of the solution at the equivalence point to calculate the concentration of acetate ion. And then because acetate ion is a weak base, we can calculate the pH using the Kb and the acetate ion concentration. And then the number of moles of acetic acid we'll go through and we'll calculate, right? So first we're going to calculate the number of moles in solution, because we need to go through and do, you know, set up a table in order to calculate the concentration of acetate ion, right? So in order to calculate the number of moles, it's just the concentration here multiplied by the volume. That gives us our number of moles, right? So we have 5.00 times 10 to the minus 3 moles of acetic acid. Hence, when we work through the table, right? So if we set up our table similar to table here. Let me show you. Right. We have the before reaction, the change based on the limiting reactant, and then after reaction. So if we were to set up this table just like that here, we would end up seeing that right, we would have, right, our before, our change, and our after. So before, we're looking at our CH3, CH, our CH3, COO minus, and our hydroxide. Right. So our before here is the 5.00 times 10 to the minus, 10 to the minus 3, and our initial here is 0, and X is our initial concentration that we need to figure out here for the hydroxide. We know that at the equivalence point, we are going to consume all of our acetate ion, right? So that we have 0 at the end. And because of that, we'll see that same increase. Oops. I hate when the pen does that. We see that same increase here. All right, so we're going to see 5.00 times 10 to the minus 3 there. And we'll see that we're going to see that same increase. So I don't have space, but we're going to see this same increase of hydroxide ions as well. And that's what this table is, this number down here to the left is showing, right? Because we have that same increase. We know that we're going to need, in the end, 50 milliliters of sodium hydroxide because, right, the reason we know we need 50 milliliters is because we know we need the, well, actually it's not written here, because if you work through the data, let me just draw the numbers out here, right? So we're going to need 5.00 times 10 to the minus 3 hydroxide in order to neutralize the acid that's there. And you can simply work backwards, right? If you know you have a 5.00 times 10 to the minus 3 moles, we multiply that by the concentration, the inverse of the concentration, which is going to be 1 liter for every 0.100 moles. Right, so we do the math, the moles are going to cancel, and in the end, you're going to see 0.050 liters or 50 milliliters of the sodium hydroxide solution is going to be needed. All right. So then we look at the equivalence point, right? If we want to work through the concentration of the the acetate at the equivalence point, right? We have to make sure, and again, this is with these particular types of problems, we need to recognize that we are adding the volume of both of the reactants, the hydroxide and the acetic acid. So we have a new volume, 100 milliliters or 0.100 liters at the equivalence point, because we've added two volumes together. So then when we figure out our concentration, we need to start with our number of moles here, right? The number of moles of the acetate, which we calculated in the table here. And we're going to divide by the volume of 0.100 liters, and shows that we have a 0.0500 molar solution of the acetate ion. Right. So once we have our acetate ion, right, we just, this is just simply our base equation, right? So if we were to simply have acetate, that acetate reacts with water to give us acetic acid plus hydroxide ions, right? If we then take our KB equation for our acetate, right, and then we can simply plug in and calculate the KB, right? If you're first, you need to calculate the KB, which is simply the KW divided by KA. You should look up the Ka of the acetic acid in a table. So this is another point that you're going to need to recognize. The acetate ion KB is not in the table. You'll only find the acetic acid in a table. You'll find the Ka. and you'll need to interconvert to the KB for this equation. So another key point for these types of problems. You can see the complexity is increasing only from the perspective that you have to recognize where you're going to get these numbers from. Where is the KB going to come from? And it's going to come from the fact that you get the Ka of its conjugate acid. All right, so we now calculated the KB here. We can then use the ice table, and they don't draw the ice table out here, but you have the ice table, right? Oops. You have your ice table. All right. Just make sure you go through your ice table. You have your we have our initial here is going to be our 0.0500 molar solution. We're going to have a change of minus x, 0.0500 minus x here. We have a none here, adding x to both sides here, right? So we end up with x out in the end, and we just simply plug that into our KB equation. We then make the assumption, again, that x is really tiny, so x is going to go away, and then we solve for x. And we're not going to go through all the calculations. You should be well on your way to understanding how to do that by now. And you see that the concentration of hydroxide ions is 5.3 times 10 to the minus 6. That'll give us a pOH of 5.28, and subtract that from 14 to give us a pH of 8.72 for this particular solution. And then you just want to confirm, because of the fact that you're working with a weak acid and neutralizing a weak acid at its equivalence point, the pH is going to be above 7, right? So you confirm it is above 7, it's 8.72, which makes sense. Questions on this problem before we do a sample?
Hey, Dr. Barbosa, I have a question.
Yep.
If we have the KB solving it the first way, why do we have to use the ice table to find it the second way?
So the KB, I mean, you're saying if we solve for this concentration here, the acetate ion, is in order to calculate pH, we need, I'm not sure if I understood your question correctly. So in order to calculate the pH of the solution, we need to calculate the quantity of hydroxide ions that are present. This first part of the problem here, the change before and after, from before to after just gives us the quantity of the acetate ion. We then have to take this acetate ion, and that acetate ion goes through a second step. So we have first a stoichiometry calculation, right? So this was the stoichiometry calculation first, and that tells us how much acetate ion that exists. And then the second one is the equilibration reaction. Whoops. Right, we have two different steps that occur here. We have the first one where we take our acetic acid, right? This reacts with hydroxide ions, and that goes in it's a one-directional reaction, right? This is not an equilibrium, where we form our acetate ions plus our water. Right. And this is the stoichiometry half. And then we have a second step that occurs where now that acetate ion, which is formed, then reacts with water in an equilibrium fashion to give us acetic acid plus hydroxide. Right, this is our equilibrium calculation. And this hydroxide here, this is what gives us our pH of our solution. And that pH is going to be, greater than a pH of 7 because we have hydroxide ions present. I have a problem here. Does that make sense? All right. So it's a two-step process whenever we're calculating equivalence points with weak acids and strong bases, or weak bases and strong acids. All right. Let's do a sample problem. All right, so here's the sample problem. Why is the pH at the equivalence point larger than 7 when you titrate a weak acid with a strong base? So when you get the answers A through E, type it into the chat box. And we'll go through. Any questions when you're working through the problem, please feel free to chime in, unmute yourself, or type it in the text box. So if you're struggling with this problem, then you have to understand, if you're struggling with any of these problems that we worked through, please set up some time to, meet with me so we can discuss and work through some of these problems on one-on-one sessions if we need to. And I can help you work through. It's easy to set up a session like this, and we can just use OneNote or a whiteboard to work through these problems. So if you're struggling, these are concept problems right now. And just make sure you understand what the concept was of what we were covering. All right, so this one's talking about, says, why is the pH at the equivalence point larger than 7 when you titrate a weak acid with a strong base? There's, at the equivalence point, remember, this is not true, because at the equivalence point, our acid, right, our HA is going to equal our base. I'm just going to list the base as, I don't know what I'm going to list the base as just RB minus maybe. Right. So that's not true there. So A is not correct. There's excess weak acid at the equivalence point, so the same thing here, right? Because the acid is equal to our base at the equivalence point, both of these are false, right? The conjugate base that is formed at the equivalence point is a strong base, right? It's not, right? In the last example, we were talking the acetate ion. It's not a strong base. Typically when we're talking strong bases, we're talking hydroxide ions, right? Hydroxide ions are the strong bases that we, one of the strong bases we discussed. And the conjugate base is not. It's going to be the conjugate base of a weak acid, which is a weak base. All right, so that's not correct either. Since most people are voting for D, I'll cover E first, right? The statement is false. The pH at the equivalence point is always 7 at the equivalence point. This is pH titration, and obviously this is only the case when we have a strong acid. 7 is only when we have a strong acid and a strong base. Right, this is the only time that this statement is true, when they're both strong. So obviously E is not correct. And then the conjugate base that is formed at the equivalence point reacts with water. And that's what we talked about in the last slide, right? You have your conjugate base, your A minus, reacts with water and gives an equilibrium to form the acid plus hydroxide ions, which affect the pH of the solution. All right, if you're not understanding why the answer was D, please, again, set up time to meet with me. Questions on that problem? Go back to the slides. All right. Before I continue, I just want to, because I don't want to freak, never mind, I'll cover it at the end. Somebody stop me at 9:15 if I keep going. Ways that a weak acid titration differs from a strong acid titration, right? So when we're talking about what are the difference between the weak acid and a strong acid titration. So a solution of a weak acid has a higher initial pH than a strong acid. The pH change, right, so that we're just talking about down here, right? The strong acid, its initial pH is lower, it's closer to 1. Weak acids, as you know, they increase in pH. So our pH increases, and that's because the Ka is decreasing, right? Our Ka of our weak acid is smaller, so the pH of that solution increases. The pH change near the equivalence point is smaller for a weak acid, and this is because of what's going on, right? If we think of that pH change that occurs, right, if we're starting higher than our end point, right, because if we're reacting it with a strong base, we're going to have the highest that we can get is the pH of hydroxide ions, right? So that pH change from beginning to end is going to be smaller, right? For, depending on where your starting point is, right? And this is talking about, that central region, of where the pH change occurs. And the pH at the equivalence point is greater than 7 for a weak acid, right? And that as your Ka decreases, that equivalence point increases, right? So we get to higher and higher pHs. And that, again, is because of the Ka equation of that reaction. What's that equilibrium going to produce out, right? If we have our of our conjugate base, our A minus, is reacting with water to give us our HA plus our hydroxide ions. When we're talking about this reaction, our Kb equation here, the Kb is going to be dependent on our Ka, right? That's equal to our Kw divided by our Ka. So the smaller our Ka is, the larger our Kb is. That means the higher the concentration of hydroxide ions that exist in the Kb equation. So our produces a higher pH. We have a higher concentration of hydroxide ions, gives us a higher pH. All right. So use of indicators. Indicators are weak acids that have different color than their conjugate base form. Each indicator has its own pH range over which it changes color. An indicator can be used to find the equivalence point in a titration as long as it changes color in the small volume change region where the pH rapidly changes. Right? So what we're talking about here is we have our indicators. We're going to look at a couple different ones. Right? When we have an indicator, if we have a strong acid reacting with a strong base, right? This is the first example here, right? Strong acid, strong base reaction. If we have a strong acid reacting with a strong base, the reaction that occurs can cover the pH change of both of these indicators, right? Phenolphthalein, right, has a color change interval between a pH of 8 and a pH of 10, meaning that, you know, it's going to have a different color, obviously, when we either going to be clear at 1 pH or colored at 1 pH, and then we'll go clear as the color changes. Usually it's going to start off colored up here, so it's going to be in this particular example, you're going to have a color at the top, right? You know, at the high pH, and then at the low pH is going to be clear. Right? So you can see as you're reaching the equivalence point, as your pH changes, as you're coming around this curve, you suddenly have this rapid change. When you have this rapid change with very, very small additions of HCl in this case, right, when you have a small addition, that phenolphthalein is going to rapidly change from a dark purple color to clear over this small, you know, range here. Or conversely, the methyl red, right? The methyl red is going to go from, I think it starts from clear and then goes to colored. Right? It goes from clear to colored here, and you're going to see that same exact pH change. Again, very small amounts of addition at the near the equivalence point. But it's still not ideal, you know, but it does, you know, you'll still get a very close answer to the exact equivalence point here. Now, if we're starting with a weak acid and we're titrating it with a strong base, as is shown here, you can see that phenolphthalein is going to work, right? Because we're starting off with that weak acid where the solution starts off clear, and it's clear just before the turn. Clear, you know, just before the turn, heading up towards the equivalent point, it's clear, and then right around the equivalence point, it starts to change color, right? So we have this rapid change in color that occurs at the equivalence point, and this is a perfect, you know, for the color indicator to show for this titration. So you end up with dark purple out in the end, right? So you can tell exactly when you're at the equivalence point. Whereas methyl red, right, we're starting off with this red color here first, and by the time we hit the curve here, we've already gone through the color change. So it's not exactly clear in this case. It goes to a yellow color, and at the equivalence point, this yellow color remains all the way to the end. So this is not an ideal indicator for solution. And you know, you can see, I mean, this is the labs that we discussed last week, went through this exact type of color point titration. Obviously, it would have been nice to have you see that, but it didn't exactly work out that way. Oh, we have a question here. Let's see. So the equivalence point is where the pH and the pOH are equal to one another. No, the pH and pOH are not going to be equal to one another at the equivalence point. It's where the concentration of the hydroxide and the concentration of the, in this case, the HA, are going to be equal to one another. So when we're talking about equivalence points, we're talking about we want our HA equal to our hydroxide. Right, so it's not going to be, and only in the case of the strong acid, strong base, are they going to be equal to one another. And then they'll be 7.0 times 10 to the minus 7th. So equivalence point has to do with the equivalent reaction. So basically you're completely neutralizing, right? So you have your HA. Oops, why does my pen do that? Right. Yeah, so you have your HA reacts with the hydroxide completely. All right. All right. So here's the slightly different titration reaction here. Right. For this titration here, we're titrating a weak base. Right. We're starting with a weak base at the top, and we're titrating down to give us with a strong acid. So obviously, and going in the opposite direction, you know, unlike the previous example where phenolphthalein worked great when we titrated a weak acid with a strong base, but methyl red did not work. When we titrate a weak base with a strong acid, right, we're adding HCl to a weak base in this case, rather than maybe, well, you can just say, for example, maybe this is ammonia, right? And this is the reaction of ammonia plus HCl, and we're titrating a weak base. You can see where the phenolphthalein range right here isn't ideal. We're going to have a color change occurring before we reach the equivalence point, whereas now methyl red is going to be ideal. And you can see methyl red will work for this titration. All right. Hopefully indicators make sense to you. You want to be on the curve where the pH change is occurring rapidly at the equivalence point with our indicator. All right, titrations of polyprotic acids. So when a polyprotic acid is titrated with a base, there is an equivalence point for each dissociation. And we can, using the Henderson-Hasselbalch equation, we can see that halfway to each equivalence point gives us the pKa for that step. Right, so if you have, as an example, I don't know what example they're using here. I don't know what acid they're using. But if you think about, let's just say we had, as an example, H2SO4, right? We can eventually get HSO4 minus, and then eventually to SO4 2 minus, right? So this is an example, right, where we're starting with a strong acid, and then in between, right, from this first range from here to here, we're seeing the conversion from H2SO4 to I'm sorry, that's not right. My bad. Right from here to there. Right. Right. So this is the first transition from the H2SO4 to the HSO4 minus. The second transition is going to be here, right? So we have two different transitions that occur. And when we're talking about our pKa's are the halfway point, right? Halfway between where we start and the first equivalence point is going to be our pKa, and then halfway between these two equivalence points is going to be our second pKa. Okay, so we have our pKa1. Man, I don't understand why that happens. our pKa1 here, and then our pKa2 there. Yeah, so I'm not sure that this graph is actually H2SO4, but it makes sense for H2SO4. This acid doesn't appear to be H2SO4. I'm not sure. This is not H2SO4. I'm not sure what this acid actually is, quite honestly. It's got a hydrogen here. This looks like somebody who didn't know what they were drawing, but drew this graph. Artist rendition of H2SO4. But it would work for H2SO4. Right. So solubility equilibria. So because ionic compounds are strong electrolytes, they dissociate completely to the extent that they dissolve. So when an equilibrium equation is written, the solid is the reactant and the ions in solution are the products. So the equilibrium constant expression is called the solubility product constant, is represented as KSP. So here we are, we're going to throw another equilibrium number at you. Right, now we're talking our KSP here. Right, all this is, right, we have our KC, really bad KC, right? So we learned about our KC equation, right? KC is just the equilibrium reaction. We talked about our, our KW, which was special for water. We talked about our Ka, which was special for acids. We talked about our Kb, which is special for bases. They're all exactly the same. Now we're talking about KSP, and that's the solubility product constant. Right? It's just another equilibrium. That's SP. That's just another equilibrium, and we're going to look at them and just, again, think of these as just normal equilibria that are applied in special cases. All this does is give us, just like Ka gave us the ability to compare acids, Kb gives us the ability to compare bases, KSP is going to give us the ability to compare the solubility of different compounds. So that's all we're looking at here. Right. So a new equilibrium constant is solubility product constant here. So let's go through an example. If we have barium sulfate, right? And we're taking barium sulfate and we're going to dissolve it. So we're taking this and reacting it in water, right? So all we're doing is we have this beaker sitting here. It's filled with water, and we throw the barium sulfate in, right? So this goes, and we're just dropping it in there. We have a little stirring rod, stirring away, and we end up with barium 2+ ions in solution and sulfate ions in solution. So at the end, after we're done with our reaction, we have this solid remaining, right? Our barium sulfate remaining there. We have our barium ions in solution, our sulfate ions in solution, and our barium sulfate that didn't dissolve sitting on the bottom. That's all that's going on here. And what we want to know is how much of the barium ions and sulfate ions are formed. And then we have to look at the equilibrium constant expression, right? So our equilibrium constant expression, you might originally, if you were thinking of this equation in terms of Kc, right? So we would have written that this is going to be equal to our concentration of our barium 2+, right, over our sulfate times our sulfate. All over our barium sulfate. So this is where we would have started in the very beginning. And then we realize, oh, this is a solid, right? So everybody recognize that this is a solid. These are aqueous. So the barium, the sulfate, the solid that remains, is no longer taken into account. So our KSP is just looking at the concentration of the ions that are formed. Does that make sense to everyone? So all you're doing when our KSP just takes into account how many barium ions and sulfate ions are formed. So it's just another equilibrium constant to tell us how many should form. And here's another example, right? Our barium phosphate, it's Ba3PO42 as a solid. This dissolves, gives us our barium ions, our phosphate ions. And you can see in this case, we have exponents, right? Our exponents are coming from the stoichiometry in the equation, right? So you need to, this is going back to when we first started talking about Kc, right? Our equilibrium constant expression, where we needed to take into account the stoichiometry. We've been working up till now for the past, quite some time with just acid base, and it's always one acid reacts with one base. And we haven't had to use our exponents in quite a while, so we need to go back, start to remember that we're using our exponents again. All right. Questions before I move on? Is KSP making sense? So obviously there's going to be a big difference in our KSP, the effect of barium ions, and the KSP for barium phosphate, because it's cubed, right? The concentration here is cubed, whereas the concentration of the effect of barium ions and barium sulfate is not. It's the first power. Right. So we'll go through a sample problem here. It says writing solubility product expressions, so KSPs. So write the expression for the solubility product constant for calcium fluoride, and then you're going to look up the corresponding KSP value in Appendix D. So if you haven't yet taken the time to look at Appendix D, we've referred to it quite a number of times. So make sure you look at Appendix D and know how to use Appendix D before the next exam, and I will talk about that in a little bit. So Annie, yes, so the exponents came from the stoichiometry. Right, so the stoichiometry of the equation, the 3 here gives you the exponent there, and the 2 gives you the exponent there. This is just as if we were doing a typical Kc reaction, right? If you remember back with Kc, oops, not Kg, Kc, our typical, oh, that wasn't Annie, that was Freddie, I'm sorry. Huh, that was strange. Popped up on my screen. Sorry. All right. Go on. All right, so like I was saying, if you haven't looked at the Appendix D, make sure you get acquainted with Appendix D, because you will be using it and you'll need to refer to it on the next exam. All right, so first part, when we're looking at calcium fluoride, you're going to apply the general rules for the equilibrium constant expression, excluding the solid reactant from the expression. And we're going to assume that the compound dissociates completely into its component ions, right? So in this example, we have calcium fluoride is going to be in equilibrium with calcium ions as an aqueous solution and fluoride ions as an aqueous solution. So if we were just simply writing our Kc equation, right, the Kc would have looked just like calcium 2 plus, right, times the concentration of fluoride to the second power, right, because we need to take that into account there. And because calcium fluoride is a solid here, it's not part of the equation. So our KSP is just listed here. If we then look up the Appendix D, we're going to see that this gives us a KSP of 3.9 times 10 to the minus 11. So it's just look it up. Pretty easy, pretty straightforward. All right. Let me do any questions? We'll do a quick sample problem. And hope this makes sense to everyone really quick. Let's do a quick sample problem. This one should be easy. It says, which of these expressions correctly expresses the solubility product constant for silver phosphate in water? So A, B, C, D, E, write your answer in the chat box. What is the KSP going to be for silver phosphate? Everyone should be able to get this, I hope. Otherwise, equilibrium problems are out the door. Unless, of course, you're sleeping because it's Monday morning and you just logged in and they're snoozing at your bedside. Is everyone there? Let's see. Everybody's still logged in. I should have about 15 answers. Still missing a couple lost souls. Yes, so the answer is C, right? So we have to just, the answer is correct, C, right? Because we have third order for silver, and the phosphate ions are, there's only, this is all going to be 1, right? So that's the first order. All the above. All right. So I hope that makes sense. Say your grade on the next exam, Hannah. Just kidding. Tough crowd. All right. Solubility versus solubility product. So we were just talking about KSP. The KSP is not the same as solubility. It's the first thing you need to recognize. KSP is the solubility product constant, or it's the equilibrium that exists between the substance being dissolved and it, reprecipitating out of solution. Solubility is the quantity of a substance that dissolves to form a saturated solution. So there's a difference. I know they sound really similar and they're related to one another. We're going to go and we're going to cover that. So common units for solubility, right? We're going to have, grams per liter or moles per liter, right? For when we're talking about solubility. So they are concentration units. Let's go and compare and look at the difference between the two. All right, so when we're talking about solubility versus the solubility product constant, right, our KSPs over here on the right are the mass of the solubility of the compound is over here on the left. Right, you can see if we have our solubility product constant on the right, we can use the solubility equilibrium, and this is going to give us molar concentration of ions, right? Because we have our, let me see, where can I write this? We have our KSP is going to equal are ions, right? Some metal with some charge to some power x times our non-metal. What do I want to list this as? Our non-metal, I'll call it B minus some product constant y, right? And that's going, we can get our concentrations from the KSP of each of the ions. Then we can use the empirical formula of the salt to calculate the molar solubility, right? The molar solubility of a compound, right? So this is going to give us our molarity, M. We then can use the formula weight to calculate the solubility in grams per liter. So you can see there's a difference. The solubility has to do with a certain quantity, a gram quantity, not a mole quantity, dissolved in a volume. So it's a concentration, but it's in grams per liter. Our KSP is dependent on molar quantities, right? Our mole per liter. So we need to calculate and interconvert between the two. So you can, hopefully that makes sense. So solubility and solubility product constants are related, but they're not the same. Third sample problem here. So solid silver chromate is added to pure water at 25 degrees Celsius, and some of the solid remains undissolved. The mixture is stirred for several days to ensure that the equilibrium is achieved between the undissolved silver chromate. Here's the silver chromate expression, formula, and the solution. Analysis of the equilibrated solution shows that its silver ion concentration is 1.3 times 10 to the minus 4 molar, assuming that the silver chromate solution is saturated and that there is no other important equilibria involving silver or chromate ions in the solution. Calculate the KSP for this compound. So I'll refer to each of these parts as we work through. So here's an example. I was supposed to animate in it bullet point at a time, but we'll do it all. So the equilibrium equation and the expression for KSP are listed, right? So we have our equilibrium expression. We have our silver chromate, right? Dissolves to give us 2 silver ions plus the chromate ion. So our KSP, because we have 2 silver ions, right? This is going to be second order here. Right. It'll be second order. Not erasing, there we go. It's really strange. All right. So it's going to be second order here, right? So to calculate KSP, we need the equilibrium concentrations of silver ion and the chromate ion. And we know that equilibrium, the silver ion concentration is 1.3 times 10 to the minus 4. So if all the silver ions and the chromate ions in solution come from the silver chromate that dissolves, thus we can use the silver ion concentration to calculate the chromate ion concentration, right? And this is going to be just simply using the chemical formula, right? So if we look at the chemical formula from the chemical formula of silver chromate, we know that there must be 2 silver ions in solution for each of the chromate ions in solution. Right? All we're doing is we have, for every 1 mole of the chromate, right, it's going to be equal to 2 moles of silver ions. Right, all we're doing is using the stoichiometry of the equation here. Right, for every 1 mole of chromate, we have 2 moles of silver ions. So we can use this as a conversion factor. So consequently, all we're doing is we're going to, take, in order to figure out our chromate concentration. Right, so if we want our concentration of chromate, right, all we're going to do is we're going to take our concentration of, well, we'll take our conversion factor of 1 mole of Cr for 2 minus divided by our 2 moles of silver. Right. And we're going to multiply that by the concentration of our silver ions, right? So all we're doing is plugging in this number, right? So we know that that number here is 1.3 times 10 to the minus 4 molar, right? So all we're doing is, you can see, we're multiplying by a half because of the conversion factor. So there we go. So that gives us our concentration here, right? We simply multiply by half. We get 6.5 times 10 to the minus 4 molar for our concentration of our chromate. So we can actually figure out our the KSP, right? So our KSP is, where's my pen here? All right, here we go. Our KSP is just going to be equal to the silver ion concentration squared times the chromate ion concentration. So we just plug those numbers in, do the math, and our KSP is 1.1 times 10 to the minus 12. So it says check, we obtain a small value as expected for a slightly soluble salt. Furthermore, the calculated value agrees well with the one given in the appendix. So if you looked up the KSP in the appendix for silver chromate, you would get 1.2 times 10 to the minus 12. And we calculated based on solubilities 1.1 times 10 to the minus 12. So this makes sense to everyone? All right, so we have another sample problem. Let's see, we have time for a sample problem. You know what? It's 9:14. So before we do the sample problem, yeah, I was going to talk about the exam. So our exam is next week. So we have, obviously, we have one more class this week. We have Wednesday class this week. And the, so we have the exam coming up, and it'll be on the, the second half of chapter 16 and all of chapter 17 will be on the exam. So I'm going to try to set it up similar to the last exam. Is there any, I wouldn't want to get strange. I got disconnected for a second. Can everyone hear me? Can anyone hear me? Okay. Everybody can hear me. Okay. That was strange. I had got disconnected for some reason briefly. All right. So the, what was I saying? All right. So I'll cover this again. So what I was saying is that the exam is going to be on the rest of chapter 16, all of chapter 17. I'm going to probably set it up similar to the last one, so that way I can still give out partial credits where you have your submission sheets, and it seemed to work. I don't know if it was that big of a headache. Anybody have any things that thought that were really difficult about taking the last exam? Feel free to unmute yourself. You'll have a sheet, that worksheet. You'll have, so everything will be set up the same. No, the typing, that all in was a pain, but there's nothing you can do about that. No, unfortunately, there isn't. I wish there was, like, everybody had tablets and we could just write everything in. That would be ideal. but we're not there yet. That's dreamland in the future. Yeah, it was just a matter. I mean, there was a little bit of typing, but I was looking. I looked at and created all of the worksheets that were scanned in. Other than that, so that's the plan. The final exam is going to cover, will be 19 and probably 20. That's the plan. I mean, we'll hopefully get through 19 and 20, but we'll see. We're not doing chapter 18. Chapter 18 is all about environment and environmental chemistry. We're not going to be able to cover that. We have to cut out stuff, unfortunately. Poor chapter 18, yes. It's just a priority thing, what you're going to need as a biochemist. Most biochemists don't go into environmental chemistry. And most biologists also don't go into environmental chemistry. So it's not as required. Let's do next Thursday. I think it was originally scheduled for Thursday. So for the Thursday after Easter. So that's the plan. So usually it gives you, even if you take all of Easter off, you have a full day on Monday to study. That's me, Annie. Yeah, we can do a review session. I mean, we'll do it. We have time to set the review session up. Obviously, we won't do it till closer to the exam. We'll do it. Maybe we can do it Wednesday evening, the night before. If we want to do another one, as long as people are going to attend. So we can do it Wednesday evening, because my guess is most people aren't going to stay till the last minute. So probably, I don't know what most people look like on Wednesdays, maybe 7 o'clock on that Wednesday beforehand. So let's schedule it tentatively for that. And if we're heading towards that, it doesn't make sense. So, other questions about the exam? Going once, going twice. All right. Let's see. So, alrighty, everyone. Have a good week. Have a good Holy Week. Talk to you later.